Okay, here we go. Lesson 2, chapter 5. All right, so what we're going to talk about today are called Riemann sums. And maybe you already guessed, Riemann is going to be a mathematician's name. So let's do a little refresher on sigma notation. How many of you have taken AP Stats? Okay, so you used sigma notation before. The equation editor that I use doesn't type these quite the way I want them typed. So this is how they should look. Sigma is a Greek letter. K equals 1. Some number on top, I'm going to make it 4. Okay, in math, sigma means what? The summation of some stuff. So we're going to add some things up. Okay, then following the sigma is a function. I'll just use a simple one like x squared. Okay, so what this means is I'm going to add up a whole bunch of x squares. I'm going to start with x equals 1, and I'm going to increase until x is 4, and then I'll stop. Okay, so it would look like this. Plug in 1 first, square it, plus, now we're going to plug in 2, square it. I'm squaring it because that's the function. Plug in 3, square, plug in 4, square, and stop. Then add it all up. Okay, so let's do it in our head. 1 plus 4 plus 9 plus 16. What's that? 30. So that would be the summation of all that. Okay? So anytime you see sigma in math, it means you're going to be adding some things up. Okay, so where the Greek letter sigma represents sum, the index k underneath tells us where to begin the sum, and the number above the sigma tells us where to end. Sometimes in math you will see an infinity at the top, and that just means that the sum is going to go on indefinitely. We'll study a particular type of sum called Riemann sums, named after the German mathematician George Friedrich Bernhard Riemann. Lived in the 1800s. Left ram, mid ram, and right ram are all Riemann sums. Okay, so look at this picture here. Does it look like what we did yesterday? Okay, somewhat, right? So yesterday we talked about making rectangles, adding up their length times width, etc., until we had a sum that approximated what? What were we trying to approximate? Area under the curve, between the curve and the x-axis. Okay, so yesterday we only dealt with graphs like that. But we know that some graphs dip underneath the x-axis. So when that happens, you're still going to use that y-coordinate as the height, but it will be a negative. So what we'll end up with is negative area.
That deletes the positive area.
It may delete it. It may be more than that. It may even cancel it if it's the same.
But we can't have negative area.
Okay, so true. Our area can't be negative, but think of it as a directional thing. So the negative area indicates that it was under the x-axis. Okay? Yes? Every now and then we don't use the same width for some particular reason. So I think they're just showing you that they may not be the same width. And if they weren't, then you would just do width of each individual one times the height. Occasionally, but not often. Usually it's the same width. Okay, so areas underneath are considered negative because they are below the x-axis. Areas above are positive. All right, if I said I wanted the net area, do you know what that would mean?
Add them all.
Yeah, add them up. So in this case, go back and look at this for just a second. If I took the negative area and that positive area and added them up, would you expect the final net area to be positive, negative, or 0?
0. Positive.
I'd say positive. I'd say we have more positive area than negative there. So I'd say the net should probably be positive. Can you think of a graph that would give us 0? Okay, keep going. What? Cosine or sine. That was fast. Think about if I had a sine graph and I went from 0 to 2 pi and I wanted that area. This area is positive. This area is negative, but they offset each other. So the net area would be 0. Okay? So your area can be positive, negative, or 0. Okay, on each subinterval, we form the product, this looks awful, I know, f of ck times delta x of k. This product can be positive, negative, or 0, depending on, come on, it looks bad, doesn't it? Yes, okay.
The function of dk times k.
Okay, very nice. Remember, we're recording.
What does it look like?
Okay.
Look like anything.
Finally, we take the sum of these products. Okay, S sub n means sum. Sigma means sum. So the sum equals the sum from 1 to some number of f of c sub k times delta x sub k. What the heck? Okay. What do you think delta x means?
You're changing it.
Okay, so this is a fancy way of saying the width of these rectangles. Change in x. How wide are they? Okay. F of a number means a y-coordinate, right?
Yes.
So it's the y-coordinate, which is the height of the rectangles. That's how we found the height of the rectangles, right? We plugged in x into the function. So this is saying add up a whole bunch of height times widths, which is the area. Okay? Because it's fancy math notation. Okay, so this is the same as area equals the sum of a lot of length times widths, or area is the summation of length times width, which is what we've been doing. This is just fancy notation. Yes? It's not always 1, no. You'll have to be told what to start and stop at. Okay, that'll be given. Okay, look at this picture versus this one. What's the difference?
The x is small.
Okay, smaller intervals, more partitions is what we call them, more slices, more rectangles. Better approximation, 100%. And you can visually see, like you can see the gaps or where it extends over, and there's less of that down here. So the more narrow we can make our rectangles, the more partitions we can create, the more accurate the approximation.
It's so small, it just gets 0.
Oh my gosh, did you read my mind, Cole?
Then
Because look.
Every area is 0 now.
Cole.
Wait, really?
Yes, really.
Oh my
Next page. The definite integral as a limit of Riemann sums. Let f be a function defined on a closed interval from a to b. So that's why I said you'll always have to know where we're starting and stopping. For a partition P, let the number c sub k be chosen arbitrarily in the subintervals if there exists a number I such that all of this is I, then f is integrable, and I is called the definite integral. Okay, let's break all this down. Summation. We're going to add up a bunch of widths times heights. Okay, but what we want to happen, ideally, is the partition width to approach 0. So we want the width of those rectangles to be as close to 0 as we could get it, which will give us a very accurate approximation. So that's what this is here for. So yes, ideally we want that width to go down as close to 0 as possible. Okay, so what is I? I is this number that we get for the area. And if we get a number for the area, then that function was integrable. And what we found was the definite integral. Integrable. So the definite integral means the area under the function. You are not too tired.
Who in their right mind sat there and came up with that?
That's why I say to use weed.
Mr. Riemann, that's right.
Mr. Riemann had no life.
He was a genius.
Like how? Why can't you just say
Coffee.
It is amazing, like how these,
How do you even start?
like it's not they made this stuff up, they recognized patterns and
Yeah,
things
right.
like that, you know? So it's, yeah, they were geniuses.
Who came up with that little symbol, sigma?
It is Greek, yeah, so I don't know
You
who,
don't know who, but if you want to make
I don't know who, but it is a Greek letter in the alphabet.
That's ancient.
Okay, here we go, there you go, you got your answer. All right, shh, listen. The existence of definite integrals. Shh. All continuous functions are integrable. Oh my gosh. That means that if it's a continuous function, we can find the area under it. Okay? That is, if a function is continuous on an interval, then its definite integral exists. We can find the area. That's all it says. Okay? All right? The definite integral of a continuous function. We don't need to read all that. It's just, again, saying, if I can sum up a bunch of rectangles, length times width, then I will have the area under the curve, which is what I call the definite integral. Notice here it's saying, let n approach infinity. Let there be an infinite number of rectangles. Sure. Okay? In practical terms, no, we can't sit there and do that. But there are other ways that we can get around it that we'll talk about soon. Okay, so here's our friend that we talked about. As usual, Leibniz had his own yet similar ways of representing the same thing. In his derivative notation, the Greek letters, delta for difference, switched to Roman letters d for differential. In his definite integral notation, the Greek letters again become Roman letters. Okay, so on the left we have Newton. Newton used the Greek notation over here. Complex. Leibniz used this. Doesn't that just look better? Okay, but it means the same thing. Remember, guys, they were in different areas of Europe discovering the same patterns at the same time, but they had different notations. This one, Leibniz, is the one that we use most often because it's just simpler. All right, so can you see that this is an elongated S? For some.
S for sum.
From A to B. That's your starting and stopping point. Here's our function, and dx means the width of the rectangles. So width, height, that's how we found the height of the rectangles. Plug it into the function.
That's not derivative.
And we go from A to B. No, it's not derivative. This is read integral. Because remember, that's what we're finding. Definite integral means the area.
Say that function.
Okay, so how many of you eat at Waffle House? Okay, next time you are there, you look on the edge of the plates.
They have a sigma sign?
Oh, that's a bad one. They have integrals all around the edge of the plate.
That's not what it is.
I don't know, but wait. Fun fact. The person who started Waffle House went to Georgia Tech.
I don't believe it. There's no way.
So I don't know if it's just a random design they ended up with.
What did you say the X represented?
The width of the rectangles.
I thought that was the snake.
The what?
What does the X represent?
Summation of.
It's basically sigma.
The S means we're going to add up from A to B, length times
They
width.
changed sigma to the S.
Means area. Okay, so here we go. Let's dissect this symbol here. Okay, so this is how we would read this. The integral from A to B of f of x dx. And what that means is, hey, we're going to find the area under this curve, between the curve and the x-axis, from A to B. That's what all that means. Okay? Yep. All right, so this little elongated S we call the integral sign. Here's our lower limit of integration, our upper limit of integration. So we're going from 2 to 5 or whatever. F of x is just the function. Like earlier we were drawing graphs of functions and finding the area. Whatever the graph is, that goes here. And then dx is representing the width. Now, we don't always use x. For example, if I have a function that is using time, I might use dt instead of dx. Okay? But dt and dx are probably the most common. Yes?
Is like the bigger number always B?
Goes from lower on the bottom, upper on the top. Okay? All right, so We know what that means now. It means find the area, which is what we were doing yesterday. Okay, so look at this problem. Those directions are super crazy complicated. What I'm going to tell you is, this is Newton's notation. I'm going to rewrite it in Leibniz notation. Okay, so what does sigma mean? Summation. There's my summation. I'm going, read in the directions, from -1 to 3. -1 goes on the bottom, 3 goes up top. What is my function? Okay, these things here, those are the variables. You got it. 3x squared minus 2x plus 5. Instead of delta x, he uses dx. And if there's more than one term, then we just put that in parentheses.
Okay.
What's dx? They didn't give it to us?
Represents the width of each rectangle.
Did they not give it to us?
Oh, no, not in this, unless you know how many subintervals and all that kind of stuff.
It says 4 divided by n.
So that is saying what, however many intervals we find, the width would be 4 divided by n. If I said find 10 subintervals, then the width of each rectangle would be 4 divided by 10.
So we're not actually doing the derivative.
No, we're just setting it up right here.
And then what if you wanted to find the sum, you'd plug -1 to 2 into that equation?
No, we'll talk about that soon. Hold that thought, Aiden.
Alrighty.
All right. Okay, so again, this is what I have been saying. This thing here means find the area. Okay? All right, next page. Okay, here is a direction for you. Evaluate this integral. That means find the area under this function from -2 to 2. What is that if I graph it?
Semicircle.
Don't peek to the left. It's a semicircle.
Can we just find it by using a semicircle?
Yes, I'm not going to use any calculus here. I'm going to use geometry. But I need to know that this means find the area. Okay? I'm going to strictly use geometry now. So here's a semicircle. I know the area of a full circle is pi r squared, but I only have half of one. What's the radius?
2.
Plug it in.
4 pi over 2 just equals 2 pi.
There's our area. And we were not given any units, so you can just say units if you want to, or square units, or just leave it. Okay, so we're just finding the area. Yes. We just did the integral. Like, that's what that means. Find the area, I did. And that's not an approximation, is it? That's exact area.
So you don't plug anything to that thing up top?
Mm-mm.
Never. You just get it.
I'm not going to say never.
Never say never. So like, why are we doing that?
Why are we doing this one? Because we don't...
Why are we doing like the little thing at the top? We don't plug anything into it. We just go straight to doing the area.
We will plug those into something eventually. I think it's tomorrow. So you don't have to wait too long. It is tomorrow. Okay? Okay. I just have faith in me, Aiden, okay? But you're hanging your head like you're defeated. Okay, all right. So negative area, we already talked about negative area. This graph here of what I'm looking for the area, that would be totally negative because it's totally below the x-axis. What do you think the net area would be here?
Negative.
Positive, negative, or 0?
Perhaps 0.
Positive. Because it cancels out. Wait, no.
I think it's going to be close to 0, don't you?
Yeah.
I mean, that,
It's not a full.
yeah, we don't have a definite answer here because we don't have a function name.
Yeah,
It's just a guess. I'd say it's close to 0. Okay. So notice it says that if we have area above the x-axis, then we will subtract the area below the x-axis. But subtracting something is the same as adding a negative, right? So if I took like the positive area and the negative area and the positive area and just added them all together, then that's how we would find the net area. Okay? All right, we're almost done. Gosh, y'all are whiny. Okay,
Overcomplicating the rectangle.
skip this rectangle for a second. You gotta build up, right? We
Yeah.
can't build down.
We are building up.
No, we are not. Trust me.
Like
We
in
are
middle school, you learn
starting with
right,
easy,
you learn-
building up.
You learn length times height. Or no, wait, this is length times width, but whatever. But
Okay.
now we're doing. Okay.
Okay, keep going. All right, so ignore the box. I'm going to come back to it in a second. Let's look at the train problem again. Remember yesterday when we had the train that was going at a constant rate of 75? And it was from 7 a.m. to 9 a.m. and we calculated the area of that rectangle that was 150, and that represented the distance that it traveled. Okay, so let's think if I were writing it as this, an integral. Okay, I'm going from what lower boundary to what upper boundary?
7 to 9.
7 to 9. What is my equation that I was using? Think back to when we graphed that. What did we graph on the y-axis? The velocity, right?
Probably.
What's the velocity? Just 75. So my function here is just y equals 75. That was that horizontal line that we drew. So that's the function, 75. A horizontal line, y equals 75. dx. That's how I would write that same problem as an integral. Okay, now, how did we solve that? Remember we had a rectangle. 7 to 9, so that was a span of 2. This height was at 75. So we said 75 times 2. Why did we say times 2?
2 hours.
Because 9 minus 7 is 2, right? Yes? Okay. So now look back at this. We had the integral of a number, a constant, dx. And that area was that number times b minus a. That's what we did. Does that make sense? Okay, moving on then. That's it. Okay, so when we have really complicated functions that we're not sure what they look like, guess what we use to find an integral? Hallelujah. Find your graphing calculator.
Do you mind going back?
This can.
I just fixed my pencil.
Yes, ma'am.
Is that what you got?
Probably. If it's if you got answers, it's working.
Yeah, but the coding could be wrong and it could be like giving me the wrong.
All right, we'll test. We'll compare in a second.
That's why I did the 7. Now his area equals 75.
Just put RAM at the bottom.
Okay, here we go. All right, where do you think integrals will be on here?
RAM.
Nope. Math. Go to that math menu. Do you see them? Okay.
Number
Hey, does anybody in here have a TI-83?
84 plus, right?
Okay, then you can ignore this. This is for a TI-83. The 84s have this fancier menu here.
Oh, found
Okay,
it.
so we're going to go to number 9,
Random integral.
and it's set up just like what we were writing.
I have a question.
Hang on. -1 up to 2. Type in your function. And then dx, and it will calculate that area for us. Yes, ma'am.
If you go to math and you go to number and int, what is that? The integral?
Uh-huh. Mm-hmm.
What, so what's the difference?
You just use the. They should both do the same thing, probably. But
That's
just
that
use
area.
math 9. I don't know. We'll look at it.
That's basically telling you that's that area.
That's the area. Mm-hmm. Without even knowing what that graph looks like.
I heard.
Okay. Now, are we usually going to use our calculator?
Yes.
No.
Why?
Remember, half the exam is without calculator.
What about half the test for this?
I'll have to look at the test again. I don't recall.
For like these, then we get to use that.
Yeah, if it's a graph we're not familiar with, that's always going to be a calculator one. Oh, what's that answer?
Hi.
Pi.
It's a circle. It's back.
You can. And then you can do the third one. All right, those are all three numbers. Answers right there.
We did it.
Are we good?
Yeah.
Okay, pretty straightforward. What are we finding?
Area.
And what is this called? A definite integral. Okay, it's called definite because there is a definite starting and stopping point. Think of it that way. There are.
Integration.
It's only like if you want 50 subintervals or something like that. Then you would use it. Go to program, find it, push enter, and then it'll walk you through it.
So where do you see this in like jobs and future stuff?
This stuff?
Yeah, like the F.
Okay, so integrals are used to total up things, right? Okay, we will use them in the next chapter? Maybe the next chapter. Maybe later in this one. I can't remember which chapter it falls in. We will use it to sum up maybe the total consumption of Coca-Cola. Do you think Coca-Cola would be interested in that? Absolutely. There's a problem that we do, the total consumption of potatoes.
Okay, what about, so that's like economics, right?
Mm-hmm.
Is there anything like more towards engineering?
Total material used to make something. Yeah. Anytime you're looking for totals and something is changing at a rate that you can find, that leads itself to calculus.
Why do we use this way instead of writing it out?
Like for area?
Yeah.
Because we don't always have area formulas. Okay.
Like you might have a weird shape.
Okay, here we go, guys.
Geometry formula.
Use areas to evaluate the integral. 3 more to do here. All right, the integral from, oh, crap, we got to hurry. From 0 to 5 of 5x. Okay, here's my function. If I graph that, what does it look like? What does it look like? Okay, y-intercept of 0, slope of 5. Okay, I'm just going to sketch a line, okay? And I'm going to go from 0 to b, some mystery number. But b is bigger than 0, so I know it's positive. What shape do I have? Okay, what is this ordered pair right here? Give me the x-coordinate. B. And what is f of b? What? 5 times b. Where did I get 5b? I plugged it into this function that is y equals 5x. Okay, so I have a triangle. Now I do have a formula for this area. 1/2 base times height. What is the base of this triangle? B. What is the height? 5b. What's my area?
3B.
You can write it 2.5 if you want. Here we go. All right, next one. What function am I graphing?
X.
Y equals x. Don't make it hard. Line with a slope of 1. Square root of x is what you're thinking of. Y equals x. Oh, I'm going from a to square root of 3a, but a is bigger than 0. So here's a somewhere down there, and here's square root of 3a.
Square root of 3 times a, not square root of 3.
Correct. The square root of 3 is in front of a. Okay, so it is a trapezoid. What is this ordered pair right here?
A and AX.
A what?
AX.
What is f of a?
X and
It's just A.
Wait. Where are we getting these letters?
Here's the equation, y equals x. So whatever x is, that's what y is. So what is this ordered pair?
3A, 3A.
Square root of 3a. Square root of 3a. Okay, now we can do our trapezoid. 1/2 base 1 plus base 2 times the height. The height is that perpendicular distance here. Okay, so I have 1/2. What is base 1? A. What is base 2? Okay, and what is the height? Square root of 3a minus a. Because it's this distance. If this was 2 and 5, then that distance would be 3.
Is that right? That's square root of 3. If you go to the straight.
Yeah, just no. Because those are
It's minus.
those yes. Okay, so we could FOIL it, but because we're running short on time, we're not going to FOIL it. But I do have this one question. If I multiply these two, what do I get? 3a squared. Okay. All right. I'm going to leave it like that. Okay. Last one. We can do it. We can do it. Find the point of discontinuity of the function, graph it, and evaluate the integral using area. Oh, I don't have time.
Oh, well.
Izzy was supposed to
Probably
have his
Izzy.
paint, right?
It's Izzy's mama. Hello. Yes, I will. Okay. Thank you. Bye. Okay. Cole, as soon as we're done, you go see Miss Armis, and then you go see Miss Pate. Okay. All right. Here we go. How am I going to find a point of discontinuity?
Five later.
Just find where it's the limit is 0.
Find where it is undefined.
Yeah.
Where's it undefined?
At 2, negative 2.
Negative 2. Okay. Discontinuous.
Oh, because
Look at the denominator at negative 2. Now, when we did limits, we did deal with problems like this. So you were right about that. And I factored when possible. And what do you notice?
Cancel.
2 plus x cancels. Okay, therefore, this graph will look like y equals what? X minus 2. So that's a line. But what happens at negative 2? There is a hole at x equals negative 2. Okay, so all that we did with limits. Okay, so now I'm going to graph it. So I'm just going to graph this line. And I'm going to graph it from x is negative 1 to 3. So this negative 2 hole in the line won't affect us. Okay? All right, here we go. Dun, 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 dun. Minus 2. Y-intercept. Okay, slope is 1. The hole is going to be over here farther than we are graphing. So here's the line. Area is here plus there. It's 2 triangles, isn't it? I have one under the x-axis. That area will be negative. Then I have this little bitty triangle above the x-axis that will be positive, and then for the sum of the areas, I'll just add those 2 together. Okay, so let's do big triangle. Area equals 1/2. What's the base? 1, 2, 3. What's the height? Negative 3. Plus the little bitty triangle. What's the base? Height is 1. So I'll add those up. So that's negative 9/2 plus 1/2. Negative 8/2 or negative 4. We did it. All right, you take your stuff since the bell's about to ring. Izzy, you take your stuff as well.